Hello students, I am Ayush Purwar and I welcome you all in this tutorial, and today I am going to discuss a very important experiment, that is the young slit double experiment. Okay, so let's start. Let me share my screen.
Okay, so let's understand the Young's double slit experiment. Okay, so what is the Young's double slit experiment? See, this is the setup of Young's double slit experiment. Here we have put a slit S and we are incidenting the light from here like this. We are incidenting the parallel light wave. Okay, okay, this is a very narrow slit. Okay, and at some distance from this slit S, this slit will work as the source of light. Okay, and at some distance from this slit we have put two another slit, that is S1 and S2. Okay, so when the wavefront from this slit will fall on this slit like this, the spherical wavefront will fall on this slit. So these two slits again will work like a source or like a secondary source of light. So now from these two sources also the light wave start emitting, start coming. Okay, okay, fine. And these two waves, the wave from source S1 and the wave from source S2 will come out and will interfere at this point P. Right? Right, great. Now let's understand what is happening at this point P. Okay. So this is the experimental setup of the Young's double slit experiment, and now we have assumed that the distance between these two slits S1 and S2 is T, that is here, right? And the distance of the screen, this is the screen. Okay, this point P is at the screen, so the screen is put from a distance capital D from these two slits S1 and S2, and the screen should be very far from this slit, means that is capital D should be much greater than small d. This D, which is the distance between two slits, this should be very small, and the distance between slits and screen should be very large. Okay, if this is happening, if this is we are assuming, then what will happen? This distance S2P and S1P, or this, let's say this is a point M, the distance MP, these three distance will almost be parallel because this distance capital T is very large compared to this small distance. Okay, so if the wave is coming from these two light source, then these all these waves will be parallel to each other because the distance is very large, the distance between screen and slit. Great. Now if the distance is very large, that means this angle that we have drawn here, this will be very small, this angle theta, right? If this angle theta is very small, then let's understand, I have drawn a perpendicular from this source S1 to this ray S2P. Okay, to this ray S2P, I have drawn a perpendicular, and this perpendicular is S1 and okay, see, this is a perpendicular, so this angle will be 90 degrees, right? Okay, and this angle is theta, right? So now let me draw here. Okay, let me draw here. See, this is the case. This is the point P, and these two rays of light is coming at this point. Okay, and there is one ray that is going like this, and this is the distance capital D, right? Now I'm saying this angle is theta, right? So if this angle is theta and these three rays, this is S1, this is S2, this is M, if these three rays means S1P, MP, and S2P are parallel, okay, these three rays are parallel, then if I draw a horizontal line here, then if this MP and S1P are parallel, then this angle will also be theta, right? And I have drawn a perpendicular from this source to this S2P line, okay, and this is S1N, right? And this angle is 90, right? If this is 90 here, then this will also be 90 here, because obviously this is perpendicular to on both of these rays S1P and S2P. right? If this angle is 90 and this angle is theta, see, then this angle I am drawing with a different color so you get a clear vision. This angle, this small angle will be how much? This will be 90 minus theta, right? Absolutely right. This is 90 minus theta. Now this I am asking you this. What is the angle between this line and this line? How much? This again be 90. This will be 90 degree in this angle, right? And this angle, this small angle is 90 minus theta, and this is whole 90. So how much is this? This will be theta, right? So this angle will be theta. That's what I want to tell. So here I have drawn this angle is theta. I have explained it here. Why? How is it theta? Because I have assumed that capital D is much greater than small d. That means S1P, MP, and S2P will almost be parallel. So we can consider that if these three lines are parallel, then this angle will be theta. Only then it will be theta. Otherwise, it will not be theta because we have considered this that capital D is much greater. Okay, fine. Now let's see if I have drawn this perpendicular S1N. So you can see this S1P and NP distance are almost same, right? Yes, these distance are almost same. So the rays that is coming from source S2 is traveling an extra distance S2N, right? Yes, that's right. Because see, I have drawn a perpendicular, so you can see from the diagram also and from the intuition also you may get an idea that S1P and NP distance are almost same. So the rays that is coming from the source S2 has traveled an extra distance S2N. So that extra distance means that extra path difference. That extra path, the rays that is coming from source S2 has traveled, right? So what will be the path difference between rays S1P and S2P? That is delta X, and I can write it like this: S2P minus S1P. That's right. S2P minus S1P means what? If I will, I have to subtract S1P from S2P. What will be left with? We will be left with S2N, right? S2N. That's right. So this will be the path difference. Now let's see how much path difference this will be. Okay. So see, this is very simple. Let's draw this triangle. I'm drawing here. See, this is S1 point, right? This is S2 point, right? This is N point, right? And this angle is theta, right? And this angle is 9. You can see from the diagram, right? And this distance is D. Again, right? Okay. So apply the formula. What formula? Sin theta will be equal to S2 N divided by D from the perpendicular to hypotenuse, right? Right, perpendicular divided by hypotenuse. This is the formula of sin. Great. So from this we can directly calculate S2N. S2N will be equal to D sin theta. That's right. S2N will be equal to D sin theta. That means path difference delta X will be equal to D sin theta. That's right. Okay. So delta X is path difference D sin theta. That is equation 1. Great. Now see, this we have calculated the path difference between two light rays, that is S1P and S2P. Great. Now what is happening at this point P? What is happening at this point P? At this point P, two light rays that is coming from source S1 and S2 are interfering, right? So after interference, either they will give maxima or they will give minima. Now what is maxima and minima? Maxima means either they will give maximum intensity or they will give minimum intensity, right? So now we have to see whether they will give minimum intensity or they will give maximum intensity after interference. So maximum intensity point we call the maxima, and the minimum intensity point we call the minima. Now these minima and maxima has other name also. Okay, maxima is the bright fringe and minima is the dark fringe, right? Okay. So now let's understand at this point P, whether maxima will be formed or minima will be formed, means whether bright fringe will be formed or dark fringe will be formed. Great. So for bright fringe, for bright fringe, the bright fringe means the maxima should be formed, means maximum intensity we should achieve at this point P. To achieve maximum intensity, we very well knew from the discussion of interference that so the phase difference should be 0, right, 2 pi, right, 4 pi, right, 6 pi, right. If this is the case, then what will be the part difference? We again know very important formula for part difference, that is delta is equal to 2 pi by lambda into delta x, right? So now put the value. Now this can be written as 2n pi. Absolutely, this can be written as. So now put the value. 2n pi is equal to 2 pi divided by lambda delta x. So we can cancel 2 pi from 2 pi, right? So delta x will be left with n lambda, right? So if the part difference is in the integer multiple of lambda, means wavelength, then maximum intensity we will achieve, means their maximum will be found, means their bright range will be found. And this, if this is happening at that point, then we say that constructive interference is taking place. Constructive interference means maximum intensity. Again, these all are names of the same thing: bright range, maxima, constructive interference. All these terms means that we are getting maximum intensity. Yes. So that means for the bright fringe, delta x is equal to m lambda, and from equation 1 we know that delta x is equal to d sine theta, right? So we can clearly write d sine theta is equal to n lambda, right? D sine theta is equal to n lambda. Okay. Now call this equation second, and this is known as the condition for bright fringe, right? Condition for bright fringe. Great. And you should remember this condition because this is important and will be used in solving numerical. Okay. Now let's see for dark fringe. For dark fringe, again, for dark fringe, we very well know that the phase difference, from the discussion of interference, you should be aware that the phase difference for the dark fringe is, for the minimum intensity, the phase difference would be 2n plus 1 into pi. That is right. So now we again know the formula between the relation between the phase difference and the part difference, that is delta is equal to 2 pi by lambda into delta x. That is right. So I will write the value of delta x, that is 2n plus 1. Pi is equal to 2 pi divided by lambda into delta x. So we will cancel pi from pi. So we'll be left with delta x equal to n plus half into lambda. So this we will achieve here. Okay. Or I can write it like this also, that 2x delta x is equal to 2n plus 1 lambda by 2. So again we know from our discussion of from equation first, we know delta x is equal to d sine theta. So we know that d sine theta can be written as 2n plus 1 lambda by 2. Now this is the condition for dark fringe. Condition for dark fringe. Okay, dark fringe means minimum intensity. Minimum intensity. As I have told you that the minimum intensity, you know from the discussion of interference, that the minimum intensity means zero intensity if the intensity of two individuals are same. And in this case, in the Young's double slit experiment, we have taken the intensity of these two individuals is same. Great. And the maximum intensity, if the intensity of two individuals are same, will be equal to 4 times of the intensity of the individual wave. Means if the intensity of individual waves are I naught, then the maximum intensity we will achieve is 4 I naught. Okay. Great. So we have achieved the condition of, we have got the condition of maximum intensity and we have got the condition of minimum intensity. That means we have got condition of bright fringe and we have got condition of dark fringe. Now, one more discussion I want to do here, and that is fringe width. Fringe width. Fringe width be represented by beta. That is, fringe width means the distance between two consecutive, the distance between two consecutive maximum or the distance between two consecutive minimum. That is known as the fringe width. Okay. Okay. Now, what is the condition for the bright fringe? The condition for the bright fringe is d sine theta is equal to n lambda, right? So this is bright fringe. Okay. Now, I want to write this sine theta in terms of the parameters that is easy to measure. Okay. So let's move back to the diagram. Okay. Let's see. This is sine theta. Yes. Let me erase all these parameters and see. This is angle theta. Yes, this is angle theta. So if I will apply here sine theta is equal to, then this will be the perpendicular ym divided by, and this will be the 90-degree angle. So this will be the hypotenuse. Means here I have assumed MC. And since I have told you that this distance is capital D is much greater than from this distance is small d, that means this MP can also be approximated as D. Okay, given the condition that capital D much greater than small d and angle is very small. Great. So we can write by M is equal to D. Okay, so sine theta is equal to, by M upon D. Okay, put this value here. Sine theta is equal to by M divided by D. Now put this value in this equation. So we will get D ym divided by capital D is equal to n lambda. So we will get D ym divided by capital D is equal to n lambda. So we will get ym is equal to n lambda capital D upon small d. This m is the distance of the bright fringe from the central point or the central maximum point. Okay. Okay. This is the central maximum point. This is the central maximum point. This is the central maxima. You can also say central maxima. So this distance by m is the distance of the bright fringe from the central maximum point. Okay. Now let's understand this. So this is the m, or you can say this is the n by n is equal to n lambda d upon capital D. So this is the distance of central maxima. This is the distance of the nth bright fringe from the central maximum. Now I want the distance of n plus 1 bright fringe from the central maximum. That will be by n plus 1. So we will put n plus 1 in place of n. So we will get n plus 1 lambda d upon small d, right? So if I want the distance between these two, consecutive bright fringes, then we have to do by n plus 1 minus yn, then we will get n plus 1 lambda d upon small d minus n lambda d upon small d. So we will get lambda d upon small d. Okay, so this is the fringe width. This is for, because I told you the distance between two consecutive bright fringe or the distance between two consecutive dark fringe is known as the fringe width. So this will be the fringe width, and we will denote it by beta, and that will be lambda d upon small d. Okay, yeah. Similarly, you can see from the case of dark fringe. Now let's do that analysis also. What is the condition for dark fringe? That is d sine theta is equal to 2n plus 1 lambda by 2, or I can write it n plus half lambda, right? So again, we know that sine theta will be same. Sine theta is yn divided by capital D will be equal to n plus half lambda. So now I can get by n is equal to n plus half lambda d upon small d, right? So this is the distance of the nth dark fringe from the central maxima. I want the distance of n plus 1 dark fringe from the central maxima. So now I will get n plus 1. I will put n plus 1 in place of n plus half, right? And lambda d upon small d. Okay. Now I want the distance between these two consecutive dark fringes. So I will get by n plus 1 minus by n. So I will get n plus 3 by 2, right? Lambda d by d minus n plus half lambda d by d. If you will subtract these, then you will see that, and this again can be written as beta because this is also the fringe width. Then you will see n will cancel out from n, and lambda d by lambda capital D upon small d will be there, and 3 by 2 subtracted by 1 by 2. So we will get only lambda d upon small d. So you can see either from the case of bright fringe or from the case of dark fringe, you are getting the same fringe width. Okay. So the formula for fringe width scale is beta is equal to lambda d upon small d. Okay. Okay. So see, this is very important formula. Okay. You should remember this formula. And very one thing is very important to highlight in this formula. I am highlighting this formula. Okay. You should remember this formula because it should be used in many numericals. And one more thing, see here, capital D is the distance from the screen from is the distance of the screen from the fillet. Okay, so it is a measurable quantity. You can take a scale and measure this quantity, right? And small d is again the distance between two slits. Again, this is a measurable quantity, right? And if you observe the interference pattern on the screen, you are getting the bright fringe and dark fringe on the screen. Then also you can measure this beta, that is the fringe width. You can measure some instrument using some instrument. You can measure the width of this bright fringe or dark fringe, right? So these three quantities are measurable. So you can measure using some scales or some other instrument. Okay. So if you know these three quantities, then you can calculate the wavelength of light. That is very, very difficult to measure. By these instrument, you can't measure the wavelength of light because this is very, very small quantity. So through this experiment, one major thing to do this experiment is you can measure the wavelength of any light on which you are doing this experiment. So this is a very, very major thing that you can do using this Young's double slit experiment. Okay. I hope you have understood. Thank you. Bye bye.